I'm gonna, I think it's, yes. Okay, yeah, it's recording now. So after knowing these definitions, if for assume for, it says for all A element, okay, let me just start here. I'll just, okay, it's fine. And then, right, for A4, if for all A element, if you have A, which is an element of real number, this is R. So if A is element of a real number, there is a corresponding number denoted by negative. This one is for negative. There is a number also which is a negative number. So this number is also element real number. It's also an element of real number. So this number that is corresponding to this one, it means that if we add them, when you say A plus, you put a bracket minus A, then your answer, you're going to get 0. So this is axiom number 4. So now when you know these axioms, you don't really have to memorize them. So in your question paper, you will find that when you check at the back of your question paper, they will write them, but you just have to know also how to use them. So you will see when we use them. So now I'm gonna go to another ones. This one, they are also an axiom. They are definition whereby they substitute back to what we are doing now. So it's just the axioms that you can use them when you have two things or when you are multiplying. Is for multiplication actually. So the first one, this one we name them M. We have M1 until M4. So this one here, if you have A and B, which are element of real number. So which are element of real number. So there exists an element also, there exists. So there exists a number that it can be A also and B, ne? And this number also, this is still the same. You see, I wrote same things here. It can be A and B, which are also still an element of that real number. So, and this A and B, we can be AB, it can be equals to BC. So AB can not BC, is gonna be ABA. So this is M1. So M2, if you have for all A and B.
Is this a new section?
This one, yes, this is a new section, yes. That those, here we talked about the axioms. They fall under the axioms, but we call them M1. They are called M1 and M2, yes. So if you have A for all A and B and C element, they're also element real number. So this A and B and C, they also have an identity in such a way that if A, let's say if A and B and C, we put brackets there, then is equals to what you can say, you can take out A and you brackets B and C. So the other thing that you must know with real analysis, we are, because you are a mathematician, we are going back to what we did in grade 1 in primary. So when we are going back in what we did in grade 1, now the difference between a learner who is in grade 1 and you who is at a university level is that now you must prove, we are working also, okay, we must prove for the uniqueness. Is this thing the true things now? Is this thing a true thing or is it not true? Because somebody can come to you, he said 1 + 1 = 3. And I can come to you and say, no, 1 + 1 = 2. But who said 1 + 1 = 2 in mathematics? That was just an assumption. That was just an agreement between mathematicians that we must make 1 + 1 = 2. But in reality, 1 + 1, it was never been equals to 2. But it's just that if you are speaking to people who don't understand maths, you don't have to talk to them like that because they will say you are crazy. So let's go to number M3. So M3 is for the uniqueness. So for uniqueness, it states that if you have an A element, also a real number. So in this element here, this A, there is a number that is 1. There is a 1 behind that number. So that's why if you say A, there is a 1 equals to A, there is a number that is unique, which is 1. So that 1 is the unique number. So which means A1 is going to be equals to A, and that 1 is also an element of real number. That's as M4, M3. So M4, let me just erase, make a new. Okay, so I'm just gonna take out this here. So M4, so M4, so for M4, we have a number that is, if we have a number that is an element of A, of real number, and this number is not equals to 0, it's not equals to 0. We can assume that this number is greater than 0, but it's not equals to 0. Then it means that there exists also a number which is A to the power -1, which is also an element of what? A real number. And this number, when we multiply these two numbers, like when you say A and A to the power -1, then you get the answer which is equals to 1. So that's the M4. So now, which means if you have to solve something like this, you can use the theorem M4. You can just state M4. So those are few things that you must know about the axioms that you must know in order for you to make a proof. So now we're going to go to order of the structure. We're gonna go to order structure. So for the order structures, you also have the ones you name them. They normally, when you name them after your proofs, you name them as O. We call them O. You can say O. They are from O1 until O4. So the first O1, the O1 state that for all, if you have A and B, if you have A and B that are element of real number, then which means there is a one statement, there is one solution that is true, is either A is equals to B, or is either A is less than B, or is either B is less than A. One of these statements that I've written here, exactly one, it must be true. So if this one is true, then it means this one, they are false. So this is O1. Is this one, we call them order structures. So number O2 state that if you have A for all A and B, which are also an element of real number. So if A is less than B is true, if this is true, if this is true, and also B, let's say B is also less than, B is less than C, is also true, is also true. This implies that, this means that A is less than what? Is less than B, is less than C. For C is also an element of what? Of real number. That's axiom number 2. So we're gonna go to.
Where did you get C from?
Okay, here we are saying, let me explain to you in the simple terms. We are saying, in other words, we are saying that A is 1. We say 1 is less than, is 1 less than 2. And then also the other statement that it says 2 is less than 3. Then this also implies that 1 is less than what? Is less than 3. So remember, when we are using A, B, and C, this A and B, we are representing numbers. Just that because we don't know which number we're going to be using, that's why I'm using A and B and
Okay.
C. So C here is just also a number that it can be in a set, any number. So with a counter example, if we have 1 that is less than 2 and also 2 is less than 3. So because of these two statements, if these two statements are true, then it implies that also this one here, the one we wrote there, is also less than what? The 3. So if we put it now, you see that it's going to be A is less than, if A is less than what? B, and B is also less than C, then this implies that if both they are true, it implies that also A is what? Is less than C, the other number. So this is just also an order structure. Is number 2. So number 03. Did you understand it?
Yes, yes.
Okay. So 03, it states that if we have A also, let's assume that we have A, B. Just because I'm using A, B, you can use any symbols. It's fine. If you have A and B element also real number, and in this A and B also element real number, if A is less than B is true, then A plus C is also less than what? B plus C. So what is the meaning of this? It's meaning that if we have 1 here, which is less than 2, then in this 1 less than 2, we decided to add 3 here. We say 1 plus what? 1 plus 3. Then this is still the same as, is also going to be less than 2 plus 3. Because if we add them, it's going to be 1 plus 3 is going to be 4, and which is less than what? 2 plus 3 is 5. So that's the meaning of M03. So the second one, the fourth one, if we have A and B also element, if we have A and B, which are also an element of real number, then if A also is less than B, if is true also, then it means that if you multiply with a number, but we're gonna use C, if you multiply it with C, then this still is still like AC is still going to be less than what? BC. This is O4. This one is for multiplication, yeah. The other one, the first one we did was for addition, and the second one we did was for distribution. So it means that this statement also, if this is true, also this one is also true. Those are A4. So this theorem, it's only going to help you to, when you understand them, you may not remember, you may not memorize them, but when you understand the logic, what is happening, you can solve something, then you go back. After that, when you're done solving, you go back to your question paper, you just name them. Oh, because without naming them in real analysis, your answer, your proof is wrong. You must state why you are saying that. What are you based on? So those were about the order structure. So the other thing that we're going to talk about now, we're going to talk about the bounds. This one is very important. You must take note of this one. So now when we talk about the bounds, we are going to talk in a set. We have if we have a set here, for example, let's say we can say 0 into 2. 0 into 2. In this set here, we have a maximum, and we can also have a minimum. So sometimes in a set, you might find that you don't have a maximum. There is possibility that you might not have a maximum and you might not have a minimum. So based on that, for us to know if we have maximum and minimum, we must use the rules of mathematics. So in the terms of a bound, so I'm gonna give you a first a small scenario so that you can understand. So let's say if we have a set E. Let's say if we have a set E for some real numbers. So this set E, it can have or it may not have may not have a maximum, a number that is bigger than. Okay, let me explain properly for you. Let's say we have a set E. So in this A, there is a possibility that there can be a number which we can call it M. So this number, it may or it may not be a maximum. It may or it may not be bigger than. Well, let's use the word bigger so that I don't confuse you. It may not be bigger than any, it may not or may not be bigger than any number in this set. Did you get the point there?
I think so, yes.
Okay. So if it cannot be bigger than, or it cannot be, it can be bigger than any number. So in a set, we have something we call it upper bound. Upper bound. We have upper bound and we also have a lower bound. So the upper bound, I will start with the upper bound. So if you have a set, this set, I'm giving you a definition. If you have a set E, then for a real number, and there is also a number M that is says to be an upper bound. This number we are said to be an upper bound. It's said to be an upper bound. That is says to be an upper bound for E. Then this means that if there is an X, if there is a number which we can call it X, which is an element of this set E, it means that X is going to be less or equals to M for all X element E. For all X element E. So this number, this number, which is element of E, it will be X is less or equals to. So this is about the upper bound. So the upper bound, when we talk about the upper bounds, is about the maximum, It's a maximum number. Upper bound is a maximum number in a set. And a number cannot be in a set, but it can be an upper bound of a set. So let me show you with this 2 and 3. 2 and this set that I just wrote here, 0 and 3, 0 and 2. So if 3 also is an upper bound of what? It's an upper bound of this set, which is 0, 2, 0 and 2. But it's not in the set of what? In this set, but it's an upper bound. So if a number, in other words, if a number is upper bound and is not also in the set that you are working with, so that set, we call it is bounded, unbounded set. So this definition that I just gave you now is for the one that I just gave it to you now is for upper bound. So we also have a lower bound. So for a lower bound, we also have, when we talk about lower bound, we are talking about the minimum. You must take it as minimum. I will just say mini. So when we talk about minimum, there is a number that is lower than all. It means that if you have a set E, there is a number, we can call it M, that is lower than all the element in E. So if there exist, let's say there exists X in element E, set E, it means that M is going to be less than or equals to X. but it will never be bigger than x. That number, it will never be bigger than x. That's all about the what? The lower bound. So the question can ask you to find a upper bound and a lower bound of a set. So let's say, for example, let me give you an example. So let's say you have, I'm gonna start with this one. Let's say you have a set of 0 and 1. This is a set. So this set, you can still write it as is the same as for x dot, and then it's gonna be 0 is less equals to x, which is less equals to 1. Eh? So now this set, the upper bound, the 1 there is an upper bound. Is equals to 1 upper bound. The upper bound of this set equals to 1. Equals to 1. And the lower bound, the lower bound of this set is 0. Ne? So why is it 1 an upper bound, and why are we agreeing that a lower bound is 0? It's because 1 and 0, they are within what? The set, inside this set. But which means this set here, it have a maximum. The maximum is what? This one, we call it a maximum, which I'm gonna talk about it later now. And then this one here, we're gonna call it a minimum. So this set, it have a maximum upper bound, and it also have a minimum upper bound. So you might get a number also the same way. I will write like this. These are brackets. This is the same as equals to, if you are writing in interval x, whereby 0 is less than x and x is less than 1. So in this set here, this set, it does not have maximum. No, there are no maximum here. No maximum, and also there is no minimum. And there is no minimum. Why am I saying that? You might think, why now 0 and 1, they are not minimum? 0 and 1, they can be also upper bound of this, because they are hard. 0, it can be lower bound, and 1, it can be upper bound. But 1 and 0, they are not included in this set. Do you get the scenario? What do you understand what I'm saying now?
Yes. Why is it not included?
It's
Why is there
because
no?
of, remember, if you use brackets like this means
Okay, I think I
less.
understand. I understand.
Less, yes. This one, it have maximum and minimum because it is less equals to. This is just less than only. So
Okay.
that's why if you write a set like this, it means that 1 is not included. If you write something, you are also doing programming, right?
Yes.
If you say if you use an if statement, I'm just giving you with this and just an example. If you say x is less than, if x is less than 1 like this, and after that, when you say cin x, for cin x, a person enter 1, and then maybe if x is less than 1, then you must say, you must print 2, then a person enter 1. 1 is not less than 1. You see, it's not less than 1, so it won't print these 2. So that's why that is exactly the same proof. That's why, like, we have this proof. This is exactly the same way you can think of this set when it's not included. So this is included. That's why it have maximum and minimum. But these two numbers, they are also an upper bound of this set, but they are not included in this set.
Can it have a normal bracket and a square bracket?
Yes, the one for square brackets is this one.
Can it have both?
Yes, sometimes you can find on a set. Okay, for example, let me give you an example. You can find, okay, this is a normal brackets. It says 0 into 1. Ne? This set it have only this set it have there is no it have no minimum, ne? But it also have what it has a maximum. Why is it have maximum? Because 1 is included. Because when we write it, it's going to be 0 is less than x, which is less than or equals to 1. So now, after explaining when you understand this, this is going to take me to talk about this one is going to take me to talk about something we're going to call it infimum and supremum. Have you read about the infimum and supremum?
No.
Okay. So now, what is infimum and what is supremum? So when we talk about supremum is the least upper bound of a set. So I'm gonna give you a simple definition of it. Let's start with if you have an M and this M is the least, this M is the least of all is the list of all the upper bound is the list of all the upper bound of E. Let's say we have a set of E, then we're going to use the word letter E of E, the set E. So this means that M is the minimum of all the upper bound. This means that this M is the minimum of all the upper bound. I will just use U, upper bound. Yeah. So what is the meaning of this? It means that in a set, you see this set here, which I draw here. I wrote there. This set, it have many upper bound. Even 3 is an upper bound of this set. Even 10 is an upper bound of this set. But the minimum upper bound of this set is 1. So this is what about this. This is exactly what I'm explaining when I'm writing this. So now when we go to this upper bound, we talk about something called supremum. Supremum, you're going to write it as SUP, supremum, when you are answering your question. Supremum is abbreviated as sub. So now, when we talk about the definition of a sub, if we have E is a set of a real number that is bounded above. If we have a set E, which is a set of real number that is bounded above, So what is the meaning of bounded above? So when we talk about the set that is bounded above, it means that that set it has like a maximum when it's bounded above. It have a bounded above. That is means that it have maximum. So this set that we have now, if it is bounded above and it's non-empty, it's not an empty, it's non-empty set, it's not an empty set. It means that this M is of the least. It means that this M, if it is non-empty and we have M, it means this M is the least of all the upper bounds. So it's the minimum upper bound. It's the list of all the upper bound. So when you write this M is going to be equals to you say supremum of what? Of E. So which means you will see when I'm doing questions with you based on the supremum. So we also have infimum. So we also have an infimum. So infimum, it states that if you have a infimum is also, it is like infimum. Let me just write it down. Okay. Infimum. Infimum is abbreviated by INF. Ne? Infimum. So infimum, it states that if you have a set which is E, and this set E is bounded below. When it's bounded below, it have a minimum. Is bounded below. And there is also an M, and there is also an M that is of the least bounded below. And we also have an M that is of the greatest or the minimum of the lowest of the what of the set of the minimum of the lower bound. Is the set is the E is a number that is the minimum or the greatest minimum of the lower bound of the lower bounds. Then it means that this M is the M that we just wrote with the capital letter is equals to infi of A, infimum of E. So this infimum, it just means that this is the lowest, this is the minimum. Now, this is the lowest number. So if we have a set, let's say this one here, the one we were doing, where is there here. Here we found out that 0 is the what is the minimum, is the lower bound of this set. So there is still number -1. -1 is also the lowest bound of this set, but it's not really included in this set. There is still -2. There are still -4 up to going downwards, but they are not included in this what in this set. There are still many of them. So that's the meaning of this infimum. So now you know that you have supremum, which is supremum, and infimum. So I have given you the definition of those two. So I'm gonna give you some examples. So if you have a set which is bounded, let's say you have a set E. If you have a set E, which is a bounded set, let's say it's an empty set. This set is an empty set. We're just gonna represent it with slash there. Then this set is unbounded. Is bounded, unbounded set here. It's an unbounded set. So for infimum of A, infimum of E, or infimum of, you can just write that to show that it's a set, empty set, is equals to infinite if it's an unbounded set. And also the supremum of it, supremum is equals to negative infinite because it's unbounded, it's not bounded. So this is the something that you must all just remember. And then if you have SE, it's a set that is unbounded above, is unbounded above. If your set E, let's say this set E is bounded, is unbounded above. Okay, let me just write unbounded. It's unbounded above. So if this set is unbounded above, it means that your E, your supremum of E is equals to infinite because it's unbounded above, the word above. But if your E, the set E is unbounded below, I'll just write the word below. it means that your infimum of A is equals to negative infinite. So those are this everything that I've given to you today. This is the basics of things that you need to understand when you start with real analysis. So which means the question they can ask you to find the infimum of a set. They can ask you to get the supremum of a set. They can ask you again if the set is bounded above or bounded below. And then they can also ask you to find the upper bound. Bounded above and upper bound is the same thing. And then lower bound is the same as bounded below. So they can ask you to calculate to prove that if it's about this one is not about the proofs. This is just the matter of you can state that it's bounded above or bounded below, and then you can also calculate the infimum and what the infimum and supremum. So infimum, now you know that infimum is if the set is bounded below is the lowest one, the lowest number that is bounded below. And for supremum, if a set is bounded above, the highest number is the list of the highest number of the bounded above. So it depends on the questions. So I thought, do you have any question that you need me to help you with now?
No.
You
The
don't? Okay.
the
So,
supremum and infimum is a bit confusing.
okay, let me, I know those ones that they little bit, let me repeat again, with the infimum. I'm just gonna type now, yeah. Okay, let me give you the definition. You don't really have to memorize the definition, but if you read this definition that I'm going to first give you now is going to be for supremum, the list, we call it a list upper bound. And then is supremum. So the definition said that if we let E be a set of a real number that is bounded above, and this set is non-empty set, non-empty, then if M is the list, if M is the list of all the upper bounds of the upper bounds, then this means that this M is said to be, this M is the least upper bound, this M is the least upper bound of E. This is the definition of the supremum. So when we write it, or you can say, or is the supremum of E. So when you write it, we say this M is equals to sub E, like that. So example, I gave you example. Let's say we have a set. This set, we're gonna start at 3 and let's say 10. So in this set here, you can see that 10 is in this set, ne? So when 10 is in this set, And then this 10 is also a maximum. It's a maximum number. It's a maximum number in this set. When it's a maximum number in that set, and then also 10 is included, because it's included, is also an upper bound. This 10 is an upper bound. It's an upper bound of this set. When it's an upper bound of this set, we also have some numbers. We have a real numbers that it can be. We can have 11. 11 can also be an upper bound of this set, but it's not included. And also maybe 15. It can be 15. It can be 15. It can be an upper bound of this set, but it's not included in this set. This set and at 10. Ne? And we also have 100. 100 is an upper bound also of this set, but this 100 is not included. So this gives us conclusion that the supremum of this set, which is sub of the set 3 and what and 10, is equals to what? Equals to 10. That is the meaning of supremum. So do you get it now?
Yes, I think so.
That is exactly when we talk about the supremum. Supremum is the lowest number, ne? That is like it can be is greater than is the maximum of this set, and it must be included. It must this number. It must be included in the set. So if we put, let's put this way. If we put it like this, you see 10 is not included in this set, ne? Because 10 is not included in this set. So the supremum of this set, if it's like in this format, the supremum of this set, the sub of that set, I'm gonna just write it, it was 3 and what 3 and 10. And 10 is not included. So the supremum of this set is going to be equals to 9. 9 is the supremum because 10 is not included, but 10 also is an upper bound of that set. So we check the last number whereby it is in the set. So the last number that is in this set is 9. So which means the least of them all upper bounds of this set. The one which is the leastest one is what is 9. You get the, do you understand it now?
Yes.
Yes. So the same thing that we are doing, it implies to what? It implies to when we are dealing with a infimum. Infimum is the lowest. The number 3 here in this set is included, né? Which means the infimum of this set is going to be what? Of A is going to be equals to 3. But now, when I say infimum is going to be equals to 3, I can argue with you that is wrong answer. Do you agree with me that is wrong?
Why?
Because of in this set here, 2 is also a minimum number. It's just that it's not included. Ne? You get what I'm saying? And also 1 is also a minimum number, but it's not included. But the problem part, these two numbers, which is not included, they are also what? The upper, they are also the lowest upper bound of this set. They are bounded. I mean, they are lower bound for this set, bounded below. So these two numbers, they are not greater than 2 is not greater than 3, and 1 is not greater than 3. So because of that, when we check now here, if it's going down there, if we are moving from this number up going down there, so the lowest number for this set we call it, if a set is like this way, we call it unbounded. It's called an unbounded set. Ne? So because this set is unbounded set, so and We have many sets that are not inside this number. So the answer for this one, for many, for infi, it becomes negative is equals to negative infinity. Do you get the point? Because there are many numbers that are which are less than what? 3. Which are also bounded below, which are lower bounds of this set. So the answer becomes the infimum of this set equals to negative infinity. So that's how you work with it based on this supremum and infimum. So just try maybe now to check the definition of supremum and read a little bit about them. Then you're gonna get to understand the logic behind. So I'm not sure, do you have a textbook for this module, or do they supply you guys with maybe a study guide on how to study, how to work with them?
I have a study guide.
Okay, so just check your study guide. You will see that everything that I've been teaching you, in your study guide, when they teach you, they won't start here. They will start with the lowest thing that I assumed that you won't have a problem with them, whereby you see maybe addition that is commutative, and then is commutative associative. I assume that those things you understand them. So when you read there, they will start with that. But the most important things that I taught you today, this is the most important things that now with this information, you can try to answer a few questions, then you will be able to answer them. So due to hours, I said to teach another guy at 7. So he might be waiting for me. So what I will give you now, this one is just it's just something that to make you see this module in another side. So I want you to write me a proof, ne? Proof for me using the axioms A1 to A4, ne? After that, you can, if you can't, I will show you how to do it. Prove for me that 1 multiplied by 0 equals to 0. So I will need you to do this proof. Just prove that 1 times 0 equals to 0. So prove the question, which means prove that is a very simple proof. If you don't understand, just go through back to those axioms. I'm going to send you the video first. Just watch the video and see how I was writing them. Prove that 1 times 0 equals to 0. I think the proof is just meant of 3 lines. It's not even hard. The only thing just you need to do is to understand the axioms and you state the axioms. Then I'm going to also send you and I'm going to correct you. If you finish it fast, then I'm going to mark it fast for you. Then I'm going to send you the video. Ne?
Is this homework?
Yes, yes. I just want you to prove for me this one using A1 to A4. That 0 times 1 times 0 equals to 0. Just try, even if you don't understand it, just read only the first axiom first and see if you can use one of the axiom to show that 1 times 0 equals to 0. So when you prove it, let me give you a hint. Ne? You're going to say let A equals to what? Equals to 1. Then, and you can also say, maybe you can also let B equals to 0. Then if A multiplied by B, then you say equals to, then you know that this can be also B multiplied by what? By A, ne? Then you state an axiom. Which axiom state that? You remember the axiom that states that this can be like that. So A times B is axiom number So this one is M what? Is M1, né? If you write it this way. So now you can assume that, okay, if you have this, if you have A, in axiom number one state that the axiom number 3, né? It states that A plus 0 equals to what? 0 plus A, né? So now if you have A plus 0, plus 0, then this one you're going to split them. So when you split them, you just check the axiom that works with this one. I can see that is axiom number number A1. So just try to check, first read those axioms, then you're gonna get, I don't just want to give you the answer now. I just want you to work it out. Then I will show you how to do it properly. Hello?
Hello?
Yes, it's just try to prove it. Just first read the axioms and or listen, watch the video that we have been doing, then try to do it, even though you don't do it right. But after reading what we have done now, you will be able to understand how it works and you will be able to answer some other questions.
Can you send the Word document too?
Okay, no problem.
Okay.
Okay, thank you.
Thank you.